morning. So today what I'd like to talk about are the properties of chiral compounds. And we'll talk a little bit about their physical and chemical properties, a little bit about their biological properties. So optically pure or single enantiomers of chiral compounds are often referred to as optical isomers. And that's because they exhibit a property of optical activity. What that means is that they rotate plane polarized light. If you ever had a pair of polarized sunglasses, you know, the sort that are good for glare off of water, two pairs, a friend and a pair, you can see this property. I took two lenses here. You may not be able to see it right here. But if I hold them up, because the polarization of the light coming through one that is matched to the polarization of the other, I see just fine through it. If I hold them at right angles to each other, the polarization of the light comes through one way, and then the other only allows polarized light in the other direction. So at right angles, you don't get the light through. If I were to put a single enantiomer of an optically active compound, like a sugar solution, say a solution of sugar or even a clear soda like Sprite, in between the two of these lenses, what would happen would be, instead of having a 90-degree angle for it to be blacked out, I'd have a different angle because the light would be rotated part way. And so this property from very early on was something that people noticed about single enantiomers of chiral compounds. So let me jot this down. So this characteristic property is called optical activity. And as I said, what it means is single enantiomers generally, because not every enantiomer, some would have a rotation of 0, and that would be very unlikely. Single enantiomers are generally optically active. Now, it's important to be able to figure out the optical purity of a compound, whether it is a single enantiomer. And there's a very simple relationship between the concentration and the optical purity of a compound and the degree of light, of rotation of light. So basically, if you call the angle to which the plane polarized light is rotated, if you call that alpha, so that, coming back to my sunglass lenses, is just, if I were again with my sugar solution, just to measure how much off of 90 degrees I need to be blacked out. That would be the angle alpha. Alpha is going to be equal to what we'll call the specific rotation. So I'll call this the observed rotation. So this is some property of the compound. Concentration, that kind of makes sense. Again, if we come back to my hypothetical sugar solution, if I have twice as concentrated a sugar solution, you'd expect it to rotate light twice as much. The concentration's expressed in grams per milliliter. finally, the path length. And that kind of makes sense. Again, for my hypothetical sugar solution, you'd expect that if I had, say, a cell or a container that was, say, about yo long with the sugar solution and it rotated light a certain amount, if I now made the container twice as long, you'd get twice the rotation. You just have a longer path and more rotation. And traditionally, this is the path length expressed in decimeters. The reasons for the choices of these units isn't so important. You've seen an equation like this back in general chemistry. You've seen this same principle in regard to optical absorbance. And the place where you've seen it is Beer's law. The same type of proportionality. Anyone remember what Beer's law is? A, what's A? Absorbance is equal to? A equals epsilon concentration path length. And it's the same basic principle. The absorbance of some solution, the amount it blocks light, is equal to some coefficient, in that case epsilon, called the extinction coefficient, times the concentration, times the path length. And again, now you could think of this, instead of being Sprite, you could think of this as Coca-Cola. If I took Coca-Cola and say I poured a little bit of it into water, I'd have a brown solution that would block out some of the light. If I poured twice as much into that glass of water, I'd block out even more light. I'd absorb more light. If I made the glass longer, if I had a longer glass and I had the same concentration of Coca-Cola, I'd have twice as much darkening if I made the glass twice as long. And so that's the same principle here. And I'm just going to recast the current equation in one way, which you're going to see it with a few extra details. So for optical rotation, typically you will see the specific rotation specified with the temperature Why is that? Because much more so than for absorbance, optical rotation will vary with temperature. It's affected by the conformation of the molecule, and that varies with temperature. The degree of having, say, gauche or anti in a butane conformation will vary with temperature. So typically one needs to specify the temperature. It also is affected by the wavelength of light. And often what people do is they use a sodium lamp. If you've ever been, we don't have them on the freeways out here in California, but have you ever been driving on a highway in the Midwest or on the East Coast and you see these yellow lamps? Those are sodium lamps. Those have a yellow line at 589 nanometers. It's actually a pair of lines. So that's called the D line, and that's what's most often used. And its wavelength is 589 nanometers. So often you will see this equation written as the observed rotation is equal to the specific rotation, this property of a compound, which is basically saying how much it inherently rotates light with conditions specified, 589 nanometer light, whatever temperature you make the measurement, 20 or 25 degrees Celsius, concentration in grams per milliliter and path length in decimeter. We'll come back, we'll be using this, so I'm going to talk a little bit later about tartaric acid and some of its properties. And so I just wanted to give us a physical meaning to this property of optical rotation, or more specifically, specific rotation that we'll be talking about in just a moment. I want to introduce a couple of terms, and then we'll have some examples of them. So one term that you'll hear is racemic compounds. What a racemic compound means is an equal mixture of enantiomers. And so what I'll say is that many chiral compounds come as 50-50 mixtures of enantiomers. And such mixtures are called racemic compounds. Sometimes you'll also hear them referred to as racemates. And these are all terms that would roll off the tongue of people who are practicing organic chemists like Buck or Johnny or myself. So these are terms you might hear or read about. A couple of other ideas, because they're important. Separations of racemic mixtures is called resolution. So, for reasons we'll discuss in just a moment, many sorts of drugs are prepared as single enantiomers. One compound interacts favorably with the body, the other interacts unfavorably, or is simply extra burden for your liver to break down. And so often in the development of drugs, it's important to get a single chiral compound, a single enantiomer of a chiral compound. One way to do this is to chemically synthesize a racemic mixture, but then to separate the racemic mixture into single enantiomers, to resolve it into its single enantiomers and just give one as the drug. And I'll give you one generalization, and we'll talk a little bit more about it and why this is true. Often chiral compounds of natural origin come as single enantiomers. So if I go home and open a bottle of wine and there are crystals on the cork, which you'll sometimes find, these crystals are crystals of a tartrate salt. We saw tartaric acid in the previous lecture. And those crystals would represent one enantiomer of the tartrate salt. We said before, I think the natural was the 2R, 3R tartaric acid. That's the one that you get from grapes. So conversely, many synthetic compounds come as racemates. Not always. It depends what you start with. But I'll give you an example in a moment. So let me start with an example of a chemical reaction. It's a reaction that you're going to learn in a little bit, but right now I just want you to look at the chiral outcome of the reaction. The reaction is called acid-catalyzed alkene hydration. You may recall that I used this reaction as an example of curved arrows and of Lewis acids and Lewis bases when we talked about chapter 3, when we talked about curved arrows and organic reaction mechanisms, or maybe it was chapter 2. Anyway, the reaction I'll show you is a reaction of an alkene, 2-butene, with water. And it's actually in equilibrium, and the product of the reaction is 2-butanol. This reaction doesn't occur on its own. If I take 2-butene, which is a gas, and I put it into water, or I put it in a pressure bottle of water, you won't see any 2-butanol on its own. But if I add some acid to the water, I'll call that H3O+. It means an acid catalyst. And this means water is the solvent for the reaction. So what I would do would be to simply have a flask with sulfuric acid solution in it and add my alkene. So we have 2-butanol here. Is 2-butanol chiral? Yes. Regardless of how I draw it, this is a tetrahedral asymmetric carbon. I haven't specified which enantiomer I get, and in fact, we get both enantiomers in exactly equal amounts. We get the racemic compound. In other words, we have a 50-50 mixture of the OH coming from the front and the OH coming from the back. And that makes sense. We start with a flat molecule. We start with an achiral molecule, 2-butene. If OH comes in from the front, we get one enantiomer, we get the R enantiomer. If OH comes in from the back, as I've drawn it, we get the other enantiomer, we get the S enantiomer. And without any handedness in the system to begin with, it makes sense that you should get both enantiomers in precisely equal amounts. Now, coming back to my tartrate example, what's the difference? Why do the grapes make 1 enantiomer of tartrate? They're unnatural and unnatural, but what's the big difference about a grape and all the biochemical machinery in a grape that goes into making tartaric acid versus the purely chemical machinery of acid and water that goes into hydrating butene? It can only use the 1 enantiomer, it can only make the 1 enantiomer. And what's the machinery? What is the machinery of a living cell? What? Enzymes. And enzymes come in a single-handed form. So you start with a single enantiomer, and as a result, it reacts to give a single enantiomer. There's a whole area of chemistry, and in fact, next week we're going to have a lecture for the graduate students like Buck and Johnny and the professors like me and Professor Rykowski on using chiral compounds to synthesize other chiral compounds, particularly as catalysts, as synthetic enzymes. This is super, super valuable because, as I said, most of the time when you're making molecules that are going to be biologically important, you want a single enantiomer. And in order to get a single enantiomer, you have to start with some chirality. You have to start with some handedness. Nature makes enzymes, but often it's not convenient to exploit natural enzymes. Sometimes people do. But often you want to be able to do these reactions in flasks on a big scale in the laboratory to make something valuable. Let me give you a couple of examples of the difference in biological properties between enantiomers. So, a nice example, an example that sometimes I've passed out to the class on little strips of paper. This year I didn't. This molecule is called carbone, and more specifically, it's R-carbone. Its enantiomer has the opposite stereochemistry. Its enantiomer, I'll draw the mirror image. You can convince yourself that this molecule is not superimposable on its mirror image. You notice that we have a tetrahedral asymmetric center here and a tetrahedral asymmetric center over here. So the molecule has a chiral center to it. The enantiomer is S-carbone, and R-carbone has the odor of spearmint. In fact, it's a component in spearmint. While S-carbone has the odor of caraway. Anyone know what caraway is? Caraway seeds? You get them on a good rye bread. They're these little seeds. They have this kind of pungent, kind of piney odor to them, a nice taste to them, and it's very different than spearmint. But these are the primary flavors in caraway and in spearmint. Now, this makes a lot of sense if you think about it. Can I get a volunteer? All they need to do is shake my hand. Somebody who's willing to come and shake my hand. All right, so I go to shake, what's your name? Evan. I go to shake Evan's hand in the normal way, and our hands fit together in a particular way. If, just like an enzyme or a protein fits it, if I offer my left hand, there's a completely different fit. And that's the whole point. The receptors, thank you, Evan. The receptors in your nose and in your mouth. Yeah, give Evan a hand. The receptors in your nose and in your mouth fit these two molecules differently, and as a result, you trigger different receptors. That's the whole interaction between a chiral biological molecule and another one. Now this becomes very, very important in drugs, and I'll give you a really insidious example of this that occurred in the 50s. And the example that occurred is the molecule thalidomide. So thalidomide in the 50s and 60s was sold as a racemate to fight morning sickness in pregnancy, to fight the nausea that women get when they're pregnant. There are two enantiomers of thalidomide. So this enantiomer with a stereocenter with a wedge coming out, this enantiomer is the R enantiomer. The other enantiomer, of course, is the S enantiomer. And by now you should see the two tricks that we can do easily for drawing enantiomers. One trick is simply make the mirror image on the blackboard. The other trick is simply invert all of the stereocenters in the molecule. So I'll use that trick over here for drawing the enantiomer. So instead of having the thalamid group coming out, I'll have the thalamid group going back. The thalamid is the group on the left. And so now I've inverted my stereocenter. And this is S-thalidomide. Now, the R enantiomer is an effective drug. It fights morning sickness. On the other hand, the S enantiomer is a terrible teratogen. It causes horrible birth defects. So by getting doses of the racemate, by getting the racemate, the easy-to-prepare compound that's formed by a simple chemical reaction, by getting the racemate, women who got thalidomide in the 50s and 60s got half of their dose as a teratogen, as something that caused birth defects. And many of the children who were born to these women were born without arms or without hands and all sorts of horrible birth defects. Finally, the drug was banned. And there are many medicines right now, in fact, most of the new medicines that you will get, you only will get as one enantiomer because it's much better to be safe and just give the effective drug than to give it with something that's potentially ineffective or dangerous. All right, so we were just talking about the biological properties of single enantiomers and racemates. Now what I'd like to do is to talk about the physical properties of enantiomers, racemates, and achiral compounds. Last time we talked about tartaric acid. We used tartaric acid as an example of how we could determine R&S stereochemistry in an acyclic system, figure out when we had a chiral molecule, when we had an achiral molecule, which enantiomer it was in that case, and then we looked at the case where we had a mesodiastereomer of tartaric acid. So that would be a good case to come back to. So we said that 2R, 3R tartaric acid was the natural isomer. And now I'm going to give you a couple of properties of tartaric acid. Its specific rotation, the degree to which it rotates plane polarized light, is 12.4 degrees. Specifically, its alpha D, the degree to which it rotates the sodium D-line light at 20 degrees Celsius, is equal to 12.4 degree angle. The melting point of 2R, 3R tartaric acid is 172 degrees Celsius. Obviously, different sort of degree, angle versus temperature. All right, based on this, I can tell you exactly the properties, these two properties, for the enantiomer of tartaric acid. The enantiomer of tartaric acid, the so-called unnatural 2S, 3S tartaric acid, will rotate light equally and oppositely. That makes sense. If the light interacts with one-handed molecule in one way, getting twisted to the right, it's going to interact with the other-handed molecule in an equivalent way, but twisting the light in the opposite direction. So the specific rotation is and must be, for 2S, 3S tartaric acid, the specific rotation is and must be negative 12.4 degrees. Now let's, for the melting point, come back to that handshake. When I shook Evan's right hand, my hand packed, fit together with his right hand in a particular fashion. If I had offered my left hand, and he had in turn offered his left hand, our hands would have packed together in the exact same fashion. You wouldn't be able to tell the packing. They pack equally well. And so this is the same thing that happens in a crystal. If you have a crystal of all right-handed molecules or a crystal of all left-handed molecules, the packing and the structure of the molecules is identical. As a result, the melting point is going to be identical. In other words, the melting point is going to be 172 degrees as well. Now, if we came to racemic tartaric acid, in other words, a 50-50 mixture of 2R, 3R, 2S, 3S tartaric acid, now we have a very different situation. For every right-handed molecule that rotates light in one direction, there's a left-handed molecule that's rotating light in the opposite direction. In other words, when the light passes through that sample, what's the net rotation? Zero, exactly. For a racemic mixture, the specific rotation is going to be 0. Now for the melting point, we come back to the handshake situation again. Whereas right hands pack with right hands in the exact same way as left hands pack with left hands, right hands don't pack with left hands in the same way. That right hand, left hand handshake had a different fit of the molecules together, just as a racemic compound and mixture of enantiomers in equal amounts packs into the lattice in a different way. A priori, you can't tell if that packing is going to be better or worse. You can't tell if the melting point will be higher or it'll be lower. In the case of tartaric acid, it happens to be that they pack better, and the melting point is 206 degrees Celsius. But a priori, you couldn't tell. If you have, the question is, can you have a racemate that's different proportions than 50-50? In that case, you would call it an optically enriched compound. And we'll come to the exact details of that situation in just a second. I want to fill out our tartaric example, tartaric acid example, just with one more piece, just to complete our puzzle here. By the way, with tartaric acid, Pasteur discovered chirality because under the right conditions, ammonium tartrate, salt of tartaric acid, will separate into enantiomers. The hands don't have to go together, right and left, into the same crystal. In some cases, the crystals will preferably form. So if you imagine a whole bunch of right and left hands, or gloves, let's say. I've got a box of gloves. In some cases, the right hand and left hand gloves won't pack together as well as right and right and left to left. And the crystals can separate, where all the right hands will go into one crystal and all the left hands will go into another crystal. That's called spontaneous resolution. And Louis Pasteur, in looking at crystals of tartaric acid under ammonium tartrate under the microscope, so under certain conditions you could get crystals that had opposite shapes to them, that had chiral shapes that were opposite, just like my hands are on a macroscopic scale. having opposite shapes, and recognize the concept that it must come from chirality of the molecules and that they were undergoing what's called spontaneous resolution. Spontaneous resolution means where the enantiomers will separate on their own into separate crystals. All right, last example. We'll take our, remember what the 2R, 3S tartaric acid was? That's mesotartaric acid. Remember, that was the diastereomer. That was the one I put up last, where I showed you the molecule had a mirror plane of symmetry. The molecule is achiral. Achiral means not chiral. What's the rotation, the specific rotation of mesotartaric acid going to have to be if it's achiral? 0. An achiral molecule, a molecule without handedness, has no optical activity. Remember, mesotartaric acid was the one where you had 2 stereocenters, and yet the molecule had no chirality. If you will, the 2 stereocenters canceled each other out, giving us a plane of symmetry. So the specific rotation is going to be 0. And the melting point, a priori, once again, like the racemic compound, I couldn't tell you what it would be off the top of my head without looking, without knowing empirically. All I know is it doesn't need to be the same as either the 2R, 3R, the 2S, 3S, or the racemate. It could be, by chance, the same as any one of those, but in fact, it's 147 degrees Celsius. And again, it's because the molecules pack differently. A person with 2 left feet packs differently than a person with a left foot and a right foot. If you had a dance floor full of people with 2 left feet, the dancing would be different than if you had a dance floor full of people with left and right feet. All right. Let's take a look at the question that was raised regarding mixtures of enantiomers. And let's see if we can think our way through this, and then I'll throw a couple of equations at you that really we're going to intuit. So a 75 to 25 mixture of enantiomers is said to have 50% optical purity. Another way of putting it is that this mixture contains a 50% enantiomeric excess. So let's take a moment to think about what this means. So if I have 100% 2R, 3R tartaric acid, we have a specific rotation of 12.4 degrees. And if I have 100%, in other words, pure 2s, 3s, and I'll just use ditto marks for the tartaric acid, we have a specific rotation of negative 12.4 degrees. And I think we're all comfortable if I have a 50-50 mixture. I think intuitively we're comfortable with the idea that that mixture is going to have no optical rotation. So now let's come to a situation where we have this 75-25 mixture. And take a moment to think about that. Figure out its optical rotation. So one way to think of that mixture is, okay, you've got 25% of the 2s, 3s, and 75% of the 2r, 3r. We could imagine the 25% of the 2s, 3s as offsetting 25%, as offsetting a third of the 2r, 3r, and canceling out. In other words, 50% of that mixture is achiral, and then the other 50%, so 50% is racemate, and then the other 50% of the mixture can be thought of as being just the 2R, 3R. And if you think about it that way, it makes sense. Okay, we have half 2R, 3R, and half racemate. It makes sense that we should see a rotation that's half of 12.4. In other words, that our specific rotation is going to be 6.2 degrees. So we can generalize this concept to a very simple equation. And I'll give you several different ways of saying the same thing. What we've intuited here really comes down to the following. The percent optical purity. So this is 50% optically pure. The percent optical purity can be thought of as the specific rotation of the sample, in this case 6.2, over the specific rotation of a single enantiomer times 100%. So the percent optical purity is equal to alpha of the sample over the specific rotation alpha of pure material times 100%. And so what we had in the example on your left was we had our sample was plus 6.2 was the observed rotation in this little thought experiment. Plus 12.4 was the specific rotation of the pure material. And if I multiply by 100%, that's going to be our optical purity for this example, and that's 50%. Another concept that's equivalent is enantiomeric excess. And that's just equal to the, so we call that percent EE, and that's just equal to the percent 1 enantiomer, the absolute value of the percent 1 enantiomer, minus the percentage of the other enantiomer. And in this particular case, here, that's equal to 75% absolute value minus 25%, and that's equal to 50%. So percent EE and percent optical purity are just two different ways of saying the same thing. How much of an excess is there of one enantiomer? All right, next time we will pick up with Chapter 6, Understanding Organic Reactions.